All right, so I am going to go over quickly probabilities and compound probabilities, expected probability events, and the law of large numbers. So let's go ahead and jump in. So probability, a quick recap, the likelihood that something will happen. So you have the wanted outcome over the total outcomes or total possible outcomes, and we express it in a quicker way as wanted over total, just because it helps you remember better. So let's try to find a simple example. The probability of rolling higher than a 4 on a dice. So you could roll 1, 2, 3, 4, 5, or a 6, but higher than a 4, right, will be a 5 or a 6. So you can express this as a fraction. Then you can divide that using a calculator to get to a decimal, and then you can multiply that by 100 if you want to get it to a percent. So fractionally, that's going to be, we have two possible outcomes or two wanted outcomes, a 5 or a 6, and then 6 total outcomes. You can simplify that to a 1 out of third if you want, but if you divide using a calculator, it's going to give you the same decimal of 0.33. Once you have your decimal, if you want to express it into a percentage, you can times that by 100, and that will give you a 33% chance of getting higher than a 4. If you were to just roll a dice once, 33% chance of getting higher than a 4. So there's two types of probability. You have theoretical probability and experimental probability. And theoretical probability is just the mathematical odds of something happening. So pure math. Experimental is what actually happened when you perform the experiment. So you have predicting versus reality. So let's get into compound probability real quick. And compound probability is when there's more than one event happening. So you have to find the probability of multiple events. So you're going to go um, event, however many events, and you're going to multiply them by in one, however many there are. So event one, let's say there, let's do this example, probability of flipping three heads in a row. So you got event one, and then event two, and then event three would be the third. So you just multiply all these together. So event one times event two times event three. And these are all the same thing we're looking for. So it's going to be the same probability for each event. But that's not always the case. And we'll see some examples later in this of some different compounds. So event one would be a 1 out of 2 chance of flipping a heads times event 2, which would also be a 1 out of 2 times event 3, which would also be a 1 out of 2 chance. So doing this 3 times in a row is going to give us our compound probability. So first you just multiply across the top. 1 times 1 times 1 is going to be 1, and then multiply across the bottom. 2 times 2 is 4, times 2 is 8. So we have a 1 in 8 chance of flipping 3 heads in a row. And if we want to get that to a decimal, let's divide, go 1 divided by 8 on a calculator. And that's going to give us 0.125. And then we got to multiply that by 100 if we want to get that to a percentage. So 12.5%. So if your probability of flipping 3 heads in a row is a 1 in 8 or a 0.125 probability or 12.5%. So when you're looking at cards, okay, because you're going to have some examples that deal with cards, and you got to know that, so per suit, each of these rows is a suit. You got clovers, diamonds, hearts, and spades. So per suit, there's 13 cards in each suit. And there's three face cards in each, right? Jack, Queen, King, and they're called face cards because they have a face. And then 10 non-face cards, right? The ace through the 10, 1 through 10. Per deck, so a whole deck, you have 52 total cards. So again, 12 face cards out of the 52 and 40 non-face cards here. So we're going to look at, do a compound probability here of drawing a king and then a non-face card without replacement. So replacement means once you draw it, you put it back in the deck. Without replacement means the card is not put back. So you pull it out and it stays out. So that will affect the probability. So let's do this example. Probability of drawing a king and then a non-face card without replacement. So we have two events. Okay, so we got event one, and then we're going to multiply that by event two. And that will give us our probability of both of these things happening in a row. So probability of event one is drawing a king first. So we're looking for a king. And then event two is a non-face card and without replacement. So when we draw the first card, we're not going to put it back in the deck. So non-face. So probability of drawing a king. Let's look at how many kings there are. So there's only one, two, three, four kings in a whole deck. So we know this is all first event's going to have a low probability, a 4 out of 52 chance of drawing a king. So we know that's already going to be a low probability, but when we add in event two, it's going to make the probability even lower. So non-face card without replacement. So we're not putting the card back. So that means we draw out the king. And so there's actually going to be 51 cards left. And we don't know how many non-faces left yet. So again, in a whole deck, there's 40 non-face cards. And we drew out a king, so all 40 of those will remain. So this is going to be our compound probability. 4 out of 52 times 40 out of 51. And let's go ahead and jump into Desmos and actually perform this calculation. So first one, we have a 4 out of 52 for event one, and we're going to multiply that by our next event, which is a 40 out of 51. And so you see our chance right there. And to get this to a percentage, that's our fractional probability. And then we have our decimal. We want to get this to a percent, so times that by 100. So that's going to be a 6% chance of drawing a king and then drawing a face card. If you want to get this into a one and how many, right? So this is 6%. So we're going to put a percents out of 100. So we're going to go 100 on top, divide it by that answer. So that's a 6% chance or a 1 in 16 chance of that occurring. So we don't have many questions where you have to convert it to an odds. I always just like to get it into a percentage. So again, I'm moving fast. I'm throwing a lot at you here. So let's keep going here. And oh, wrong one. Not sure what's going on with the Zoom here. Trying to share the keynote, but it's saying it's paused. Okay, and we're back. So you're going to have a few questions on the expected probability of events. So expected probability of events is going to be the theoretical probability times the number of events, and that's how many events you could expect to occur. So if we're looking to roll a 3 on a dice after 500 rolls, how many of those should we expect to get? So here we're not going to be converting to a percentage. We're going to find our decimal probability and we're going to multiply that by the number of events. So rolling a 3 on a dice after 500 rolls. So theoretical probability of rolling a 3 is a 1. There's only one 3 on a dice, right? And there's 6 possible outcomes for our wanted over total. So for expected probability of events, you just got to convert this to a decimal. And we're not converting to a percent because we need to multiply the number of events, which is 500, by this decimal. So let's go ahead and go 1 divided by 6, which is 0.166. Repeating, we're just going to go 0.167 for fast math, times 500, and that's going to give us our expected probability of events. So times 500. So based off these odds, that's going to be 83.3. So you can't have a 0.3 event. So that means roughly there you should expect, if you were to roll a dice 500 times, you should expect 83 threes. Pretty much 80. The pure math odds would be 83 of each after 500. But of course, you know that that's not what would actually happen. And that segues us into the law of large numbers. So the law of large numbers states that the more actual or trial events you have, the closer the outcomes will get to the theoretical or expected probability. So the expected probability of events would be actually closer to its like what it should be the more trials that you do. So for instance, um, sorry, real quick. The Zoom is not filming this very good right now. So again, the more experiments you do, the closer the outcomes will be matched the theoretical probability. And let's just say probability of rolling higher than a 4 on a dice, which is a 0.33 or 33% chance of that happening, which we found right here. Or sorry, no, we found that right here, 33 or 0.33 chance. So the law of large numbers states that the more rolls you do, the closer the actual outcomes will match this line. So let's look at what that would look like. So let's say we rolled a 2. So that's below a 5, and then a 3 below a 4. So that's not a 5 or a 6. And then we just keep rolling below 4. So but then we finally get a 5. And then we get a 5 and then a 6 and then a 6. And so we're getting closer, but what will happen is that eventually the more rolls you do, the more it will approach and it will get closer and closer to this line. So these gaps will get smaller and smaller with each roll that you do, because randomness, the random streaks will get more and more just approach the theoretical probability. So you can see that we start off with these big swings. Here we're not even close to the line, and then we get closer and we cross it a few times. But over time, the more you do, and this would be 100,000, but after a million, it would be almost right in that line perfectly. So that is the law of large numbers. We know that casinos are built off of the law of large numbers because they have games that are structured at a 3 to 5% skewed in the house favor. So a lot of players playing a lot of games over time, the casino's experimental outcomes will become very close to the theoretical probabilities of their events. So for instance, blackjack, you have like a 47% chance to win, 47 or 48. So if you play a million times, right, you'll probably win only 47, 48% of the time. So that 2% difference is what casinos pocket as like their profit. And it's based all off the law of large numbers. So let's do one more. You're going to get an event like this. Which is more likely, event 1 or event 2? So you just got to find the compound probability of each, and then the one that is more likely will obviously be the bigger probability. So more likely, so rolling a 3 on a dice. So first find your 3 events for each. All right, so you have a 1 out of 6 chance of rolling a 3 times event 2, which would be a 1 out of 6 chance again of rolling a 1, times on event 3, you can roll a 1 or a 3, so you have a 2 out of 6, or we'll simplify that to a 1 out of third chance. So we'll find the probability of this, and then let's compare it to the probability of this, drawing 3 hearts in a row without replacement. So we're not putting them back in the deck. So you can see hearts here. There is 13 hearts, right? 1, 2, boom, 13. So we got for event 1, you're going to have a 13 out of 52 chance times event 2, 3 hearts in a row without replacement. So we're not putting them back in the deck. So that would be then 12 out of 51 because we are not putting them back in. So each time we draw, we can't put that card back in. And event 3 would then be 11 out of 50. So we're going to compare both of these and see which probability is higher. So let's go back into Desmos. And so we'll do first the dice. So 1 out of 6 times 1 out of 3 times, or sorry, 1 out of 6 times 1 out of 6, right? Because we had to go 3, then 1, then a 1 or a 3, which was 1 out of 3. And so let's get that to a percent. So a little bit less than 1% chance of that happening. And now we're going to go 13 out of 52 times 12 out of 51 times 11 out of 50. And let's get that into a percent, times it by 100. So you have about a 1.29% chance of that happening, and then a little bit less, 0.92 of the first. So the more likely scenario is actually going to be this one. It was starting off, I would have guessed this one would be more likely, but this one, based off the theoretical probability, is actually more likely to occur. So I threw a lot at you there. I hope that this helps you with the quiz, and best of luck.